Okay, let's just take a look at example problem unit D2, the very first example problem of unit D2, conservation of linear momentum, page 3. Okay. This is a horizontal jet of water exits a nozzle with a uniform speed v1 equal to 10 feet per second. It is going to strike this vane and then is turned through an angle theta and gets out. Okay? So keep that in mind. This is the vane which is not moving. So fixed to whatever this thing is, attached to this. So it's not moving. If it's not moving, you're going to have a reaction force involved. So let's determine the anchoring force, which is equal and opposite to the reaction force. Actually, force developed due to this change of momentum. So in order to put this vane in place, not moving, you need to, of course, support the vane by applying the force in horizontal direction and vertical direction also. So what are those anchoring force needed to hold this vane stationary? Important thing, let's ignore gravity and viscous effects. Okay? So before I actually take a look at the solution, I want to show you, first of all, video. Okay. So this is a video I believe I showed you already in the class, but let's take a look at it again. This is the water turbine. Okay. This is the nozzle, and then water jet comes out and hit the vane. This is the turbine vane. And because of the time rate of change of momentum, it is going to create the force. Force is developed on this vane and eventually start pushing this vane forward and then start spinning this water turbine. So water gets in and hit this vane and starts moving. Okay, this is the water turbine. So once again, let's go back to the program here. So let's just take a look at this figure here. Okay, so the situation here is this is one of the turbine vane. And then water is shooting off from this nozzle, hit this turbine and change the direction and go out. As a result, the force is developed. Okay? So we are going to analyze this problem in two stages. Stage one is, okay, how much force is developed in order to start moving this turbine vane, which is this example problem. And then later on, once the turbine starts spinning, then how much force you need to maintain spinning. So two-stage process. Okay. So obviously this is the situation of turbine with a turbine vane. Actually, you have a series of turbine vane attached. Now initially, turbine is not spinning. So one of the turbine vane experiences this water jet coming in and hit the vane. Initially it's not moving until it is going to develop enough force to move this turbine vane. Okay? So how much force do we need? That is the force equal and opposite to the force called the anchoring force needed to hold the vane stationary. So you need to develop equal and opposite, actually a little bit bigger and then opposite direction of force in order to push this turbine vane and start moving. Okay? So we are talking about how much force do you need to kickstart the turbine, which go against the force, which is essentially force due to friction. that once the turbine starts spinning, in order to sustain the spinning, how much force you maintain, continue to supply the force to keep spinning the turbine. So, having said that, enough said, I mean. So, let's just pick up this turbine vane, and turn it around, and then let's take a look at the single turbine vane. This is the free body diagram, obviously, of this turbine vane. As you turn this into free body diagram, of course, you need to provide forces. These forces, this subscript A stands for anchoring force. So obviously this anchoring force has two direction components. Component in x direction is called FAX. Component in z direction is called FAZ. Okay. Remember, force is a vector, so it's very, very important to define your own coordinate system to begin with. Do not forget about this. So this is your Cartesian coordinate system, direction x, direction z. Now I chose this coordinate system simply because z is usually taken as elevation or height or altitude, which is the opposite direction of gravity, g. Okay? So this is the direction of gravity. Okay. So one thing I guess you probably notice immediately is, wait a minute, is this a really proper direction of FAX? In order to support this turbine, how do you need to support? You need to support the turbine from that direction, and also you need to support the turbine in this direction. Obviously, this is probably opposite. Now, in this case, I know that, but sometimes you probably never know what is the proper direction of anchoring force. So this is essentially initial guess. Initial guess, you can do that, and typically initial guess, if you have no clue of which direction of the force should be, you just guess it, guess in positive coordinate direction. That's what this problem provides you. So this is the initial guess in the positive coordinate direction. So FAX, FAZ, since you have no clue which direction is positive FAX and FAZ, you just initially guess. This is a positive direction, okay, good. But obviously I know this is probably opposite. So suppose if you do wrong guess at the initial guess, what happens? You probably get negative value. Okay, so let's find out if we can really get the negative value. All right, so first of all, I want to define fixed control volume since this is not the moving turbine vane. So this is control volume, fixed in space. So this is the control volume. You include the turbine vane and the stream of water. Then as you define your control volume, you're going to automatically define control surface. This is a control surface. Let's call control surface 1. Let's call this control surface 2. Actually, control surface 1. Control surface 2. This is incoming control surface. This is outgoing control surface. As you define control surface, next step is, of course, you are going to define outward unit normal vector for each control surface. So this is outward unit normal vector N1, and 2, which indicates outward unit normal direction of control surface 1, control surface 2. This is incoming velocity v1, which we do know the magnitude. Magnitude is given 10 feet per second. This is outgoing velocity v2. Velocity is vector. Outward unit normal vector is also vector. Okay. So now we are going to apply governing equation momentum. Okay. One of the very important thing about momentum is a vector. So this is the governing equation given. Let's be careful. This is velocity. This is volume. It's not the same thing. Okay, so this is momentum equation. Momentum equation is vector equation, as you can see. So this is not the single equation. This equation has a component, in this case, component in x, component in z. So this is actually two equations in one package as a vector form. Okay, so we're going to start from here. This is a steady flow. Steady flow really means that within the control volume, momentum of the fluid doesn't change over time. So this is a steady flow. This term drops off. Okay? Now the problem doesn't really clearly say if this is a steady flow or not. You can always ask me a question in exam saying, is this steady flow or non-steady flow? Can we assume it? Unless it is a solution to the exam problem, I will usually tell you, sure, you can assume steady or you cannot assume steady. Okay? So if this is 0, this equation of course becomes integral over the control surface v rho v dot n dA is equal to summation of the force. Okay? So this is basically momentum, flux in and out. Right hand side is the forces acting on this control line. So let's, before moving forward, summation of the all forces. So remember, we talked about lots of different kind of forces we have to think about. First kind of force is usually anchoring or reaction force. Okay. So this is a Newton's third law of motion. Whatever the force applied, you always have equal and opposite reaction force. This time, this is called anchoring force. Force due to delta P, pressure difference. Now, oftentimes, between in and out of the cross section, if you have a pressure difference, suppose if this is higher pressure, this is lower pressure, of course, you're going to create a force in this direction. If it's opposite, you're going to create a force in the opposite direction. In this particular case, let's think about that. This is the free jet throughout. So the pressure here is a 0 gauge. Pressure everywhere is 0 gauge. So there's no pressure difference between inflow, outflow control surface. So you can ignore this one. But sometimes you cannot ignore this one, you need to include that. Typical example is jet engine. Sure, jet engine has pressure difference. Okay, obviously. In that case, you have to include this one. Force due to pressure difference. The other one, force due to viscosity. If you include the viscosity of water here, of course, you're going to create the force due to skin friction. Okay. One more. This is body force. Body force is typically force due to gravity, or oftentimes if you have a flow under very heavy, strong magnetic field effects, it is also oftentimes called body force. In this case, if you include the weight of this water inside of the control volume, of course the weight is specific weight multiplied by the volume of water, you need to include this one. This is how heavy your fluid is inside of the control volume. Okay, so let's go back, take a look at problem statement once again. Okay, so the problem statement says two things. Number one, neglect gravity. Okay, and neglect viscous effects. So let's go back here. So that really means that you can ignore this and you can ignore that because the problem statement says so. Okay. If the problem statement says include the gravity, that means you have to find out the volume of water inside of the control volume that is going to create the weight. Weight is a force in z direction. That must be supported by this force also. Okay. And also, as I said, this is also zero because as you take a close look at it, this is zero gauge pressure everywhere. Pressure is everywhere zero gauge. So there's no force created due to pressure difference between in and out. Okay? So really, this problem, the only force you need to include into the equation right hand side is anchoring force, which is those two. Those two. Okay? Good news for you. Not always this is true. So later on you have to be very careful. Every single problem you need to do you need to come up with a check sheet to check all of those forces. How can we include this force, that force? This force can be ignored or need to be included. You have to be very careful about that. So let's move on. So this equation really is the two equations because you have a two control surface. Control surface 1, control surface 2. So this is really integral of control surface 1, velocity B1, density rho is rho of water. Good news is density of water is probably constant. In this case, it's an incompressible liquid fluid. And of course, this is B1 dot product N1, dA1, cross-section area here. Okay? Assuming this is a circular cross-section water jet, it's probably true. This is a control surface 2, B2, raw water, B2 dot product N2, dA2. Right hand side is of course only anchoring force, those two. So right hand side is F anchoring force. Here we go. Okay. Interestingly, this is a still vector equation. Okay, it's not a single equation. This is actually two equations in two directions, x and y direction. Okay. So should I open up? Yeah, let's open up. So this one has two equations. One of them is x direction. Let's call this x momentum. So this equation's x direction component is integral CS1 this is going to be u1. What is u1? This is a velocity v1's x direction component. Let's take a closer look at it. Okay. So right here at the control surface 1, you have a velocity incoming. So this v1 is of course u1 in x direction I plus w1 z direction k. Right? Velocity is a vector. Keep that in mind. Just a general expression. Note. Velocity is a vector. So for any Cartesian coordinate system, in this case, in this x and z plane, velocity can be represented by velocity component in x direction multiplied by unit vector in x direction plus velocity in z direction multiplied by unit vector in z direction k. This is a general expression of velocity as a vector on x-z plane. Let's keep that in mind. From that perspective, this is velocity v1 and this is x direction component of v1. Now obviously this is 0, isn't it? There is no velocity in z direction at the control surface 1. It's only in x direction. That's good. You're actually making it easy. Not really so at the control surface 2, isn't it? So control surface 2, so this is a control surface 2. So at the control surface 2, this is the velocity v2. Okay. Obviously, this v2 is broken down into two components. Component in x direction. That is u2 I. Velocity in y direction. This is w2 k. So you have a two direction components of v2. Okay? This is a situation here. This is a situation here. Okay? So at the control surface 1, you have only u1 in direction x. At the control surface 2, you have a u2 and w2 in direction x and z component. Okay? Let's be careful. So in x direction only, this is u1. Okay? Multiplied by rho water. That's just a, water. v1 dot n1. If you take a dot product, this is a scalar in integrated over cross-section area A1 plus integral CS2. CS2 in x direction you have u2. That's the velocity u2 here. Again, density of water. Dot product v2 dot n2 dA2. Right hand side is equal to force in x direction. Force in x direction is Fax, isn't it? So this is equal to Fax. This is x momentum. So this is the equation picking up on the x direction component here, called x momentum. Of course, we have a z momentum. So z momentum is integral once again CS1, control surface 1. Z momentum is W1. Rho water, once again multiplied by B1 dot N1 dA1 plus integral control surface 2 W2 rho water B2 dot product N2 dA2. This is equal to force in z direction, FAZ. Well, so this equation really is two equations in x and z direction. Okay. Important point. Like I said, this W1 is 0 because the velocity at control surface 1 has only x direction component. So this W1 is 0, isn't it? No, that means this term drops off. W1 equal to 0. So this is 0 here. So z momentum is only this. Alright? Good. Okay. Before I move on, I really want to do something. Before I move on. Okay. Usually, when you try to solve momentum problem like this, you really also need to apply continuity. Then continuity will provide you some additional information. It's almost always true. So I want to apply continuity. To see if the continuity equation gives you some additional information. Remember, continuity coming from unit D1. I hope you remember. d dt integral CB, rho dB plus integral CS, rho B dot N dA is equal to 0. So this is continuity equation from unit D1. This is a steady flow, so this term drops off, this term comes in. Now this rho is a rho of water, it's constant everywhere. So this rho goes outside of this integral, then you can divide both sides by rho and get rid of this one. Okay, you can do that because this rho is constant. If this is airflow, you cannot do that, okay, be careful. Density doesn't change throughout the flow. That's why this rho drops off. This goes outside of integral. You can divide both sides by rho. 0 divided by rho is still 0. So this equation is integral over control surface P dot N dA is equal to 0. Okay. Before moving on, I'm going to set up a small tiny table. You don't have to do this, but it's a good idea to do that to begin with. So this is a small tiny table I'm going to set up. Make sure I don't make any mistake here. Control surface 1, which is this case. Control surface 2, which is this case. Okay. Control surface 1 is here. B1 is incoming. Of course, you have outward unit normal vector N1. This is control surface 2. B2 is outgoing. Of course, you have outward unit normal vector N2 is like this. So what I want to know is, at control surface 1, what is U1 is equal to? What is W1 is equal to? Of course, W1 we know it's 0. We know that. So what is B1 dot N1 equal to. I'm going to do the same thing here. Control surface 2. What is U2 equal to? What is U2 equal to? What is W2 equal to? What is B2 dot N2 equal to? So I want to make sure I just double check at each control surface what are those properties are. So first of all, U1 is essentially, just the magnitude of it. So U1, let's call this magnitude of B1, which is, let's call this B1. We do know this is 10 feet per second, it's given by you, okay? If you take a B1 dot N1, what happens? This is incoming flow, so if you take a dot product between those two, you're going to get minus sign comes out. So this is actually minus B1, which is the magnitude of incoming velocity B1. Okay, so make sure you figure out those. W1 0. Okay. How about this? What is U1? What is U2? U2. Okay. Oh. This is theta, isn't it? Theta is defined as this angle. Okay. Right. So if this is theta, what is U2 equal to? The magnitude of U2 is V2 cosine theta. So essentially B2, this is the magnitude of velocity B2 times cosine of theta. So this magnitude, let's call that B2. So So this is, let's say, B2 cosine theta. So this B2 is magnitude of velocity B2 outgoing. What about W2? W2 is B2 sine theta. Is that right? Okay. What is B dot N? B2 dot N2? Well, if you take a dot product between B2 and N2, this is in the outflow, same direction. If you take a dot product, it just becomes the magnitude of B2. So this is B2 plus. Okay? So this is quite convenient. You don't have to do this all the time. Once you get used to it, you don't have to. But it's probably a really good idea to begin with. So let's go back to continuity equation. So this is actually integral CS1 B1 dot N1 dA1 plus integral CS2 B2 dot product N2 dA2 is equal to 0. So this is two control surfaces. Okay. Then what's B1 dot N1? Oh, you know that. It's minus B1. Then if you integrate over the control surface 1, this is A1. So this becomes that if you take integration. What about B2 dot N2? That's B2, isn't it? Then integrate over that, it's going to be A2. Oh, okay. Oh, what do you mean by that? This really means that B1A1 is equal to B2A2. This is just the flow rate, isn't it? So this really means that the Q1 equal to Q2. So flow rate incoming is equal to flow rate outgoing. That's what the continuity says. Sure enough, this is the steady incompressible flow. Same go in, same go out continuity. So here is a big observation. Suppose if you see the cross-section area of control surface 1 doesn't change, So cross-section area of this water jet remains constant throughout. So flow gets in, just the turn gets out. It doesn't change the cross-section. If cross-section area A1 equal to A2 is equal to A, what is the conclusion if A1 equal to A2? Well, that means B1 equal to B2. B1 equal to B2 equal to B. B1, we know. Magnitude of B1 is, let's go back here, 10 feet per second. Let's give it. So, this really gives you good information. This is 10 feet per second. So the magnitude of B1, magnitude of B2 are the same, and then both 10 feet per second. Oh, that's good. That's nice. So this, that. B1 equal to B2 is equal to B, which is equal to 10 feet per second. We do know that from continuity. Oh, this is additional really good information came from continuity. That's nice. Okay? So, I hope we have enough space. So, I'm going to move on, picking up from x momentum and picking up from z momentum, finish up those two equations, find out FAX and FAZ. Okay? So, let's begin with x momentum once again. So x momentum equation, u1 is essentially b1, which is b, right? So this one is b. This is b. This is the density of water. b1 dot n1 minus b1, which is minus b. Okay? Then you integrate over cross-section area A1, which is essentially A. Okay? So this is the first term. What is the second term? U2. U2 is B2 cosine theta, which is B cosine theta. Then density of water. Multiply by B2 dot N2, which is B2, which is B. Then integrate it over area A2, which is A, which is equal to FAX. Okay? Cool. So I can finish up this one. So this really means that FAX is equal to, if you simplify all of those, it's going to be minus b squared rho water cross section area A plus b squared cosine theta rho of water cross section area A, which is equal to minus b squared rho of water cross section area A 1 minus cosine theta. So I just want to plug in the values here, which is minus 10 feet per second, this thing square. Density of water is 1.94, so that's per cubic foot. Cross section area is given 0.06 feet square. 1 minus cosine theta. Right? If you plug in all of those values, the conclusion is minus 11.64. 1 minus cosine theta. So this is a function of cosine theta. The unit is probably pounds because everything is feet and seconds. Okay? So this is the anchoring force required in x direction, which is minus. Why it's minus? No. This really indicates the direction of the original guess is wrong. So that means, hey, now I realized the direction of anchoring force FAX is in fact this direction. Oops, sorry. Initial guess was wrong because I got a minus sign, okay, for my body. Alright, so now let's find out FAZ. FAZ is coming from this. Yeah, sure. This one is 0, so only this one. So FAZ is W2. What's W2? W2 is B sine theta. B2 dot N2, just B. Ah, I forgot the row. Sorry. Row water. B2 dot N2 is just a B. What's there? Cross section area is A, which is equal to FAZ. So, is FAZ? Yeah, FAZ is that. Right? So, this is B square rho water sine theta times A. So let's just plug in 10 feet per second square. Density is 1.94. So that's per cubic foot. Sine theta. Cross section area 0.06 feet squared. This is also again a function of theta. This is 11.64 sine theta. Again, the unit is pounds. Okay? So here's the conclusion. So if you have a situation like this, turbine vane is under the jet of water incoming and hit the turbine, turn the angle theta, flows away. If that's the situation with the given cross section and speed of free jet given, how much force is developed, which is equal and opposite to how much anchoring force do you need to keep this turbine vane in place, which is in x direction, this is the value, in z direction, this is the value, both function of theta. So if the theta is given, which is the angle of water turn using turbine vane, you can determine how much force is developed, which is equal and opposite to the reaction, or in this case, anchoring force. Right? Now, one thing I have to kind of emphasize is, obviously, the actual force is this is FAZ, then now you know this is the FAX. Direction is actually negative x direction. This is anchoring force. So this is anchoring force. Okay? So this FA can be found by square root of FAX squared plus FAZ squared. So this is the magnitude of anchoring force required, and also you can determine what is the angle here, of the anchoring force required. Okay, obviously you can take inverse tangent of those two forces to find out the angle. So this is the entire picture of what kind of anchoring force do you need. This is equal and opposite to the force developed by incoming water. Okay? So let me tell you, this is the simplest possible example problem in Unit D2. So Unit D2 problems are not easy. You have to spend some time, apply this equation and oftentimes continuity on every single detail, especially pay special attention for the condition of each control surface, what's going on. It's really easy to make small mistake and screw up your solution. So let's be very, very, very careful. Okay? Let's stop here.